Hello and welcome to JHEP's lesson on types of formula. This is mainly suited for OCR, but it is suited for all other examples, including the IB, and probably around America and all of them, because this is a fundamental topic that you do need to know if you want to pursue a chemistry degree, or even if you want to do A-level chemistry at all, because whoa, yeah, it's just very fundamental. So we've got two types of formula over here, and you obviously might have seen it right now, and it's empirical and molecular formula. We're going to have a look at both of them, but first let's have a crack on at empirical formula. So this is the OCR defined version of it. Other examples may have something different. I know that for Edexcel, for some reason, relative atomic mass, you say divided by the 1/12 of the mass of the atom of carbon-12, and in OCR we have compared to. So there might be different things, but here's the OCR one. Empirical formula is the simplest whole number ratio of atoms of each element in a compound. This is the most important part of this sentence. Okay, this will usually give you 2 marks, but if it gives you 1 mark, this is the core of the apple. If you do not have this, you will not get that mark. Okay, it is very important because empirical formula tells you the ratio of, or the proportion of, each element in that substance. Like for example, if we had I don't know, if we had I don't know, NaOH, right? I can see this might be the empirical formula, but I can see that for every 1 mole of sodium, we have 1 mole of oxygen and we have 1 mole of hydrogen. Okay, if this was H4, I know this is wrong. We would have 1 mole of sodium, 1 mole of oxygen, and 4 moles of hydrogen. So the empirical formula tells us the proportion of each element in the compound. The reason why we use it for giant structures such as graphite and diamond and such, if you actually did count the molecular formula, or did write the molecular formula, we would be here for ages. If you think about how big diamonds can actually be, like if you want to buy a big diamond ring for your wife, that if you really wanted to write down the molecular formula for it, which is the actual number of atoms of each element in that compound, it would be thousands upon thousands upon probably millions and billions, mate. So empirical formula is there just to show the proportion of elements in that compound. Okay, either ionic and covalent, important. So let's say I went into a laboratory and I found 10.1 grams of a solid, and then I found out that 4.1 grams of calcium, 1.2 grams of carbon, and 4.8 grams of oxygen made this 10.1 grams of a solid. And we need to use this information to calculate the empirical formula. So how would we do that? We need to remember that empirical formula tells us the proportion of each element in that substance. So, or the ratio, if you want to write it, if you want to say it like that. So what I would do personally, is to write down the just to symbolize that we've got a proportion of calcium to carbon to oxygen. Remember, in maths, we have these dots to symbolize ratio. So we know that we've got 4.01 grams of calcium, 1.2 grams of carbon, and 4.8 grams of oxygen. This next thing we need to find out is actually how many moles do we have on each one. And there is a certain formula that we use. I call it the solids equation because we use it for solids. And it is n, small n, equals small m over big MR. Okay, MR, like that. That means the mole equals the mass of the solid over the molar mass, the MR. So, or the atomic mass. Yes, yeah, it should be AR, but never, don't worry. So, we've got the mass over here. And all we've got to do to find out the mole is to look at the periodic table, which is over here. I can't remember what solid we're looking at, calcium. And to look in group 2, because it's in group 2. And we have the MR being 40.078. So if we put that here, 40.078, we could see that we could round that up to 40.1. The reason why I did that, because look, it looks easy on the eye. We've got 401 here, 401. It looks easier, and it will be easier to calculate as well. When it comes to empirical formula, it's not, at this stage, not that important to get it very accurate. I think on the periodic table, on the data sheet, it will not be like 30, like for oxygen, it won't be 15.9994. It would, or whatever it is, 15.9994, I was right. It would probably be 16, okay? So it would be good if you just leave that 40.1. For to find that out, we'll calculate it. I could tell you for free that 4.01 divided by 40.1 is 0.1. So for calcium, for carbon, we know that the MR for carbon is over here, is 12. It's 12.0107, but we can round that down to 12. It doesn't really matter. So that would be 12 grams. 1.2 divided by 12, I could tell you that for free. That would be 0.1. Oxygen. I know, and you probably will just know off the top of your head as soon as you finish AS, that it is 16. You almost probably know that. If you still don't know where it is, oxygen is in group 6, and it does say 15.9994, but in your OCR datasheet, or Edexcel, or AQA, or whatever, it would probably be 16. So 4.8 divided by 16, again, I can tell you that for free, is 0.3. So now, are we done? No. No, we're not, because over here, it says the empirical formula is the simplest whole number ratio, and that's what a lot of people forget. It is the whole number. These are decimal numbers, not whole numbers. So what we need to do, we need to divide it by the smallest number here, which is 0.1, to get up to 1, because any number divided by itself makes 1. Okay, and we have our proportion. So for every 1 molecule of calcium, we have 1 molecule of carbon, and we have 3 molecules of oxygen. Okay, the most scientific way of writing it is CaCO3, and you might know that is calcium carbonate, and that will probably be, you probably saw that in your GCSE. Let's have a look at a harder question. So we've got this solid, and we do not know the weight of it, we do not know the mass of it, pardon me. All we know is that this compound has this composition. We've got 40% of this composition being carbon, 6.7 being hydrogen, and 53.3 being oxygen. And we know that the MR, the molar mass, is 180.0. Right, so we need to use this information to find out what the empirical formula is. Well, what we do first is we have got to find out what the MR of carbon is relative to this, how much the MR of hydrogen is, and how much the MR of oxygen is. So what we do, we find 40% of 180, and so we do 180 divided by 100 times by 40 equals 72. So we know that the MR of carbon is 72. Hydrogen, here we go, 180 divided by 100 times by 6.7 is 12.06. For oxygen, we have 180 divided by 100. I know there's an easy way to do it. Times it by 53.3, and we've got 95.94. Now, we have got the MR of it, but not the mass and not the moles. So what we do is we have a look at each AR of each element, which is carbon, which is 12, oxygen, which is 16, and hydrogen, which is 1. And we try to find out how many times can we fit the AR, which is the atomic mass, of carbon into 72. Okay, so let's take this away. Let's move this. So we've got the AR of carbon equals 12. And we've got the MR of this one equaling 72. So how many carbon atoms are in 72? What we do 72 divided by 12, or you know that 6 carbon atoms make 72. Okay, so we know that it is C6, okay, because it can fit in 6 times. For hydrogen, we know that the AR of hydrogen is 1, and we know that the MR of all of it is 12. So how many can fit in here? Well, 12 can, because if we have one, well, I'm not going to draw a picture for you, but we know that 12 of these hydrogen atoms, which equal 1, make 12. So we know it's H12. For oxygen, the AR of oxygen equals 16. We know the MR of it, the proportion of it, should equal to 96. Okay, we're rounding it up. So the question is, how many times can 16 go into 96? Let's try that. 96 divided by 16 is 6. Okay, and there we have it. We have, wait, we're not done yet, by the way. We have C6H12O6. Now, we should be done, but we need to find the empirical formula. So what we need to do, like in ratio, we need to find out what number, what multiplication table, what highest one anyway, has 612 in it, okay? And that's the 6 times tables. So we can divide all of this by 6 to make CH2O. Obviously, there are different ways of doing it, like for example, saying that assuming that we've got 100 grams of this compound, and then finding out that there's 40 grams of carbon, 6.7 grams of hydrogen, 53.3 grams of oxygen, and then using, what's this? Oh yeah, and then using the N equals M over MR to find out which one. But this way at least tells you what the molecular formula is, and it tells you what the empirical formula is. So it's a good shot. But this is the general rule that you should follow. Percent to mass, mass to mole, divided by small, times to whole. Easy thing to remember. Okay, so we know that the molecular formula, this is the standard definition for it, is the actual number of atoms of each element is present, and we have to use it for alkanes and alkenes and for organic hydrocarbons, so organic chemistry basically. And we need to use it so that we know the order, we know how to rearrange these atoms in an order. Say for example, we've got I don't know, C4H10, right? We know that there's 4 carbon atoms and 10 hydrogen atoms. So we know that we can rearrange them in that way. But if we simplified that into the empirical formula, making C2H5, this is not going to reflect the way which we can rearrange these atoms over here. Okay, so that's why we use molecular formulas for simple compounds, especially when they've got such small numbers. So let's go on to the question very quickly because I'm going very out of time here. So we've got benzene, which we'll learn about in A2, Unit 3. Benzene has an empirical formula of CH. A scientist deduced that benzene has the MR of 78. What is the molecular formula? Well, what do? We know that molecules of carbon plus molecules of hydrogen must equal to the MR of 78. So, we need to look at the periodic table to find out how much does one atom of carbon weigh. And I'll put quotation marks on weigh because it's all relative to each other. So carbon is 12, right? 12 plus, and we know that hydrogen is 1. So we know that it all equals 13. So now, what we do, we multiply this. This is my trial and error sort of thing. We multiply it until we get 78, until it all adds up to 78. So, say for example, well, I'm not going to multiply it by 2 because I know that 24 plus 2 makes 26. So I'm not going to do that. I'm going to multiply it by 6. Okay, and whatever you do to this side, you do to the other. Okay, because it's an empirical formula. So that means for every one molecule of carbon, well, I keep on saying molecule, sorry, one element of carbon, or one atom of carbon, we have one atom of hydrogen. So we cannot multiply this by 6 and multiply that by 3 because that is totally wrong. So we multiply both of them by 6. And we've got 12 times 6 makes 72 plus 6. And voila, that makes 78. So we know that we need to multiply this by 6. Okay, that would lead to 6 carbon atoms and 6 hydrogen atoms. Okay, if you want to draw that, it would look, it would probably, I can't draw a hexagon I can't draw a hexagon properly, so I'm not going to embarrass myself like that. Okay, that's what benzene looks like. Obviously the ring's a bit thicker, but anyways, don't worry about that. So that is what the molecular formula is, C6H6. This came from an exam paper, F321 in June 2010. This looked really hard because the way that they phrase it is really, people faint at the size of it, but some of the information is actually unnecessary. It's just there to throw you off. Okay, but let's do this first. The relative atomic mass of tin is 118.7. First thing we do, we have a look at tin. Okay, I always do that. It's SN, by the way. It's 118. Okay, 0.7. That is fine. So we know that tin is on the periodic table. The reason why I'm doing this, you'll see why. Define the term relative atomic mass. If it was 3 marks, we need to write in specific order and in correct spelling and grammar and everything, because it's an easy 3 marker. The weighted average mass or the weighted mean mass of an atom of an element compared with 1/12 of the mass of an atom of carbon 12. Okay, weighted average mass, 1 mark. Compared with 1/12, second mark. I think, yeah, an atom of carbon 12, third mark. Okay, very important. Again, as I said with Edexcel, they would say divided. To my knowledge anyway. So that was easy. That's got nothing to do with what we're doing. No, it's the second part. Tin ore, known as cassiterite, I can't say it properly, so forgive me, contains an oxide of tin. This oxide contains 78.8% tin by mass. calculate the empirical formula of this oxide. You must show your working. There's nothing else here. So now, we know that Sn covers 78.8%. So where does the other 21.2% go? This is where we reread the question. Tin ore, known as this compound here, we do not need to know this, okay? It's not in the periodic table, to my knowledge. It could be. Contains an oxide of tin. Oxide of tin. What does oxide mean? We've got oxygen. That's why we have oxide. Okay? Oxide, oxygen, oxide, oxygen. So we know that the second part of it, oxygen, must take up 21.2%. The only reason why I'm stressing this is because lots of students don't actually read the question. They skim read it. They take all these hard words and they think, oh my gosh, this is something which I've never seen before. And then, before you know it, they've lost the mark. Okay, I did this as well. When I did this exam paper, I was thinking, what the hell is this? I mean, 78.8%. Where does the other 21.2% go? Because I did not read the question. So it's important for you to actually highlight it as well, and to actually know what an oxide is. Okay, just because it doesn't say oxygen does not mean it does not contain oxygen. Okay, it says oxide here. It contains oxygen. So we know that the composition by mass is just percentage, how much of it is in, how much of tin is in this compound. So we've got 78.8% of it. Okay, let's assume that we've got 100 grams of this compound. Okay, we can assume it's 20 grams. It doesn't really matter, but 100 grams, we use that because we can say that for tin we have 78.8 grams of it, and for oxygen we have, should have done it like that. For tin we have 78.8 grams, and for oxygen we have 21.2 grams. And it's fairly simple. We use the solids equation. So for Sn, we know that is 118.7, and for oxygen we know it's 16 because I've been keep on babbling on about it, and we can calculate it. 78.8 divided by 118.7, that makes 0.66. Let me extend this page. 0.67, let's say. And what's it? Oxygen 21.2 divided by 21.2 divided by the wonderful 16 to make 1.325. Right? Now what we do, as the old limerick goes, we're dividing by small now. Where is it? Over here. We divide it by 0.67. And your answer would be, I know it's a big mess, I know, sorry. I'm not the tidiest. It will be 1, 2, goodness knows what. 1.325 divided by 0.67 is 1.97. Let's say 2, okay? It needs to be a whole number, remember? And that's the wonderful thing about empirical formula. Yeah, we can actually round it up to the nearest whole number. So we know that for every 1 atom of tin, we've got 2 atoms of oxygen. And so therefore, our answer will be SnO2, tin oxide. Yeah? Where is it? Well, it doesn't even say tin oxide. That's another thing. But yes, that is it for... Is that it? Yes, it is. That is it for the types of formula. I know it's a very long video, but I hope I've explained everything. Yes, there you go.